Hello, everyone. Welcome to the first official video lecture of Calc 3. So we're going to start in Chapter 12, 12.1, and 12.1 is all about 3D space. Okay, and this is kind of easing into the concepts of Calc 3. Calc 3 is really just the same concepts as Calc 1 and 2, but we're moving up into higher dimensions. Okay, and really 3D space is that first higher dimension we can go to. Okay, so what kind of concepts are we talking about here? Let's kind of revisit some of these concepts from Calc 1 and 2. So in Calc 1, maybe I saw a lot of stuff like this. You know, I had a function f of x, and we said f of x is equal to y. Okay, what does this mean? Okay, I have some input x, right? My independent variable that I'm plugging into a function f. And really the function f is, we could think of just as a rule that, you know, takes this x and pairs it up with this y, okay? Now, when we say functions of a single variable, that means, okay, we're just plugging in one single number x into my function, and I'm getting out one single number y, okay? So that's what we're used to. We're used to having a single number / variable that we use as input for our function. So an example would be, let's say I'm a jeweler and I have a bracelet to sell, and maybe the cost of gold is fluctuating, right? So maybe this bracelet's just made completely out of gold, and one day the price of gold is, you know, $10 an ounce or whatever. And okay, so that would mean one day my bracelet has a certain price, and then maybe the cost of gold doubles. Okay, so maybe, you know, the next day my bracelet would cost twice as much. Okay, so we can think of the price of my bracelet, my output, as a function of the, you know, kind of market cost of gold or market price of gold. Okay, so, and maybe it's not, you know, directly one-to-one or whatever. Maybe there's some function f of x that takes my kind of market value of gold, plugs it into some function, and then I get my bracelet out, the price of my bracelet out as output. Okay, so what are we dealing with here? Okay, what's my input? Well, my input would be just some number, right? The market price of gold. So what's my input? My input is just my price of gold, which is just some real number. So that's, you know, somewhere on the number line, right? And just a little side note, we need to get used to this notation here. This R, this kind of bold-faced R, which I usually, you know, write, and it's pretty standard notation to write with kind of a second line on the left side. This means the set of all real numbers. Okay, so all the possible numbers, right? Positive, negative included. So basically, this is the number line, all the numbers on the number line. Okay. So what I'm saying is my input is just some number on the number line. I plug it into my function and I get some output, right? And again, that output is just some number, which is also on the number line. Now, okay, I got two number lines, but when I try and graph my function, that's kind of where I end up with R2, okay? We say R2, not R squared. So this is kind of a number line, my output's a number line, and then my graph would be R2. What's R2? Well, that would be the XY plane, or the kind of two-dimensional plane, right? Like this is my one number line would be one-dimensional, and then my graph in the X and Y plane would be two-dimensional. So that would be R2. Okay. So essentially R2 is just all the points of the form XY. Which we could write like this. Okay. We'll talk more about notation like this later on. Okay. So to reiterate, my input is a single number on the number line. My output is a single number on the number line. But when I graph the function, right, what's the graph of my function? It's basically a visual way to represent like me pairing up an x with a y. So this graph is saying, okay, I'm pairing up this x, let's see, this x with this y, because that's, if I draw up to my number line, okay, that's or draw up to my graph, that's where I would be on my graph. Okay. So the graph of my function, even though it's a function of a single variable, the graph of my function is in R2, right? So I have input in R, output in R, and my graph is in R2. Okay. Now, what kind of stuff did we do in Calc 1 and Calc 2? We did limits, continuity, derivatives, integrals, and so on. And let's look at the case of derivatives. Okay, these derivatives, finding our derivatives was really kind of based on, there's a lot of intuition and function built in from these points in R2, right? Let's say I wanted to find the slope of the line between these 2 points, right? Well, this is a point in R2 right here. It's got a, let's say, x2, y2, and this is a point in R2. Let's call it x1, y1. So what's the slope between those 2 points? It'll be y2 minus y1 over x2 minus x1, right? And then the derivative is this idea, okay, we're taking the limit as these points get closer and closer together, right? But key to finding this derivative and kind of the intuition behind it is just being able to work with these points in R2, right? How did I find this slope? I had to kind of find the y coordinate of that point here, the y coordinate of this point here, and then divide by the x2 minus x1, right? So I need to be able to work with these points in R2. Okay, and that gave us our kind of geometric intuition behind what the derivative is and so on. So as we move into Calc 3, we're going to deal with the same concepts. And if you're, feeling a little lost, don't worry. This is just a quick overview. So in returning to that bracelet example, okay, we said before, okay, I had a bracelet and the price of gold is fluctuating, right? And that's going to determine the price of my bracelet. Well, what if my bracelet is made of more than just gold? What if it's made of gold and diamonds? And the cost of both of these is fluctuating, right? So then let's say Z is the price of my bracelet and X is the cost of gold and Y is the cost of diamonds. Then I could say, well, the price of my bracelet is a function of, the market price, market cost of gold and diamonds. So now instead of having a function with a single input, we need to have a function with 2 inputs, x and y. Okay, so we could think of, instead of thinking of it as 2 inputs, we could think of it as an input in R2. Okay, meaning I have a point in R2. Okay, where this component is the cost of gold and this is the cost of diamonds, and I plug that into my function. Okay, so I'm plugging a point in R2 into my function. And again, my output is going to be a single number. It's going to be the price of my bracelet, right? So how would we represent this? Okay, now kind of similar to what we had before. Okay, now I have a point in R2, right? So now instead of having a number line, my input is going to be somewhere on this XY plane, this R2, this space R2. And now my output is still going to be just a number on the number line. Okay. So what would the graph look like? Well, I have a 2-dimensional input and a 1-dimensional output. So that would give me a 3-dimensional graph, right? So my input, let's, think of this in 3 dimensions, okay? Let's say this this is the x-axis, this is the y-axis, and this is the z-axis. Okay, think of this x and y, these x and y axes, these two here. Think of these as forming a flat table, and then this z-axis is coming straight up out of the table like a flagpole, if you will. Okay, so this is kind of hard to imagine. It's hard to draw in 2D, but try and imagine this as best you can. Oops. Okay. So my graph would be in 3 dimensions. Okay, so maybe my input would be this XY plane here, this kind of horizontal plane. And then my output is somewhere along this vertical axis. Okay, so what would a graph of that look like? What would the graph of a function look like in this 3 dimensions? Well, in 2 dimensions, I would just have like a simple curve, something like this. But in 3 dimensions, I'm going to have something a bit more complicated. Okay, so for every point in this plane, it's going to be matched up with some height, some output along the vertical axis. Okay, so let's do it in blue. So maybe for this point here, this point in the XY plane, think of the let's say this is at the coordinates 2, -1. Okay, maybe that pairs up to a height, a z coordinate here. Okay. And then maybe this point here, let's call this 2, +1. 2, +1. Maybe this pairs up to some z coordinate here. Okay. So maybe you're seeing some 3D now. And then I could do the same thing. I could pair all these points in my XY, my horizontal XY plane with some elevation. And maybe it kind of weaves some nice, kind of like a blanket, right? Okay, and maybe it has borders, but maybe these borders actually don't exist. Maybe my surface just kind of extends in all directions. But hopefully you see how this is kind of a 3D surface. Okay. Well, actually, it's a 2D surface in 3D space, right? Like this is like a very thin, infinitely thin blanket, but it's not just a line. It's got a some depth to it. Okay. So that's what a graph in 3 dimensions would look like. And this is something you can easily find pictures of online if you need some more intuition. Now we can still talk about derivatives and integrals for this, right? So in Calc 1 and 2, we were talking about derivatives, integrals for something. Okay, this is just our 2D plane. We had derivatives and integrals for something like this, okay? Where we said, okay, maybe the derivative is kind of the slope of that tangent line, right? Well, we can still talk about derivatives for something like this. Maybe I have a point on my surface here. I could still talk about, the derivative here, but it's going to be a bit more complicated concept, okay? But the idea is still the same, right? The derivative here was essentially the limit of y2 minus y1 over x2 minus x1. And I had to be able to work with these y coordinates and x coordinates. Same thing goes here. If I want to find a derivative here, whatever that looks like, I need to be able to work with the points in R3. And that's kind of what I've stated here. We can still talk about the derivatives and integrals of that type of function, but it's going to have a slightly more complicated interpretation. So as I said, for a normal function, this would be a function from the real numbers to the real numbers. So a function with a single variable input, which is what we're used to from Calc 1 and Calc 2. Okay, so a function from R to R. So for that normal type of function we're used to, we had to consider or work with points in R2 to get an idea about these operations like derivatives and integrals. On the other hand, let's say my input is now in R2, okay, so I'm working in higher dimensions, which is what I'm doing in Calc 3. Instead of working in, talking about points in R2, we need to talk about points in R3 to get this idea of derivatives and integrals and all that. And chapter 12 is really just the basics before we even talk about derivatives and integrals. It's really just talking about points in R3, okay, how we draw them, how we add them together, and so on. We got to be able to do all of that before we can do anything complicated like derivatives or integrals. So that's what chapter 12 is all about. Okay. So now I've kind of set the stage. So now let's move on to some actual material. So let's just talk about 3D space, and we're not even talking about functions. We're not even talking about the multivariable functions. We're just talking about the space. And I'll try and draw some contrasts with R2. Okay. So again, R2, this is pronounced R2, not R squared. Okay, this is 2 dimensions. You can think of this as 2 dimensions, okay? Okay, and then R3, 3 dimensions. Okay, so again, R2 is all the points of the form x, y, where x and y are real numbers. So we could say if we were going to write this in set notation, we could write it like this. So the braces mean that this is the set, okay? This is saying, okay, that this is the set of all ordered pairs x, y. And then this colon we could interpret as meaning such that, okay? And then we have x and y are in. This means in. This kind of backwards E means in. So x and y are in the real numbers. Okay. Okay, so that'd be R2. And what does R2 look like? It's got an x-axis, y-axis, and they're at 90 degrees from each other. And we got a positive x-axis, or excuse me, positive y-axis, negative y-axis, positive x-axis, negative y-axis, or negative x-axis. Okay, now let's compare that with R3. Okay, so R3, if we're going to write the set notation stuff, would be all ordered triplets, not pairs. So all ordered triplets such that x, y, and z are in the real numbers. Now, what does it look like? It's 3 axes. Okay, so we got an x-axis, a y, let's see, an x-axis, a y-axis, and then this z-axis. Okay, and just like with R2, everything's got positive and negative, right? Now, you might be asking, hey, okay, why do we draw R3 like this with the x-axis over here, y-axis over there, and how do we decide which way z goes and all that? So why do we draw R3 like this? Okay, so let's address that real quick. So by convention, just meaning basically just because, we draw the x and y axis, say, excuse me, draw the x and y axes like this, okay? And just by convention, we usually put x coming out this way, kind of out of the page, y going that way, all right? And then this would be the positive side, and the negative side would be kind of going back behind the page. Okay, so this much is by convention. And then, we have the z-axis, that's going to be coming straight up, okay? Okay. So that's kind of what this next block here is. I kind of left a space for it. Okay, this is the z-axis. Let's copy and paste here. And now we need to add in the z-axis. That's what I'm saying here. Okay, so we've done that. Now, why, let's see, which way is positive going to be going? Well, positive is going to be going upwards. And negative is going to be going downwards. Now, why do we, it might seem intuitive why we do that, but there's this mechanism at play called the right hand rule. Okay, so basically, if you pointed your fingers of your right hand, let's say you pointed your fingers, let's say you kind of had the fingers of your hand, let's say this is your hand, right? And let's say you had them going in the direction of the positive x-axis, and then you curled them counterclockwise towards y. Okay, which way would your thumb be pointing? Okay, well, your thumb would have to be pointing this way, right? Upwards. Okay, so that means the positive direction of our z-axis should be going that way. And this might seem like a weird rule to use, and it doesn't, it's not going to make much sense to you guys at this point, but this is going to be a rule we use in later sections of the chapter when we start getting into cross products. Okay, and so that's why we make this the positive z-axis. Now, if it's intuitive to you, that's fine. That's great. Okay. Now, how do we graph points in R3? So let's say I want to graph the point P equals 1, 2, 1. What would that look like? Well, just like in R2, I'm basically going to follow my directions. This is this first coordinate. When I have this ordered triplet, first coordinate is going to be my x coordinate, second coordinate is going to be my y coordinate, third coordinate is going to be my z coordinate. Okay. So 1, 2, 1 means I would move 1 unit. Remember, this is my positive direction, positive direction, positive direction. So 1, 2, 1 would tell me, all right, I'm going to move 1 unit in the positive direction on my x-axis. Then 2 tells me, all right, I'm going to move 2 units in the positive direction on my y-axis. So right now I'm here. And then I want to move 1 unit in the positive direction with my z-axis. So I would end up with a point like this. Okay. So if I drew a line from the origin to my point, look like that, and then I could draw this little triangle here. It's a right triangle. Okay, so try and picture that in 3D. So this is like I have an XY plane here, and this point is just like a little bit elevated from that plane. We moved 1 unit upwards along the z-axis. Okay, so pretty straightforward how we graph these points. So these numbers here we call the coordinates. Okay, the x coordinate, y coordinate, z coordinate, and so on. And so this system is the 3-dimensional rectangular coordinate system. So when we had a 2-dimensional plane, and we said this was x and this was y, okay, these are Cartesian coordinates, also known as rectangular coordinates. And then remember, we had other coordinate systems, right? In Calc 2, we talked about polar coordinates, where we had r and theta. We're going to see some similar stuff in Calc 3, but in later chapter. But we call this standard coordinate system, we call it Cartesian coordinates or rectangular coordinates. So we're used to it in R2, and then this is just the same thing in R3. So we call it the 3-dimensional rectangular coordinate system. Now, we could talk about coordinate planes. So what is a coordinate plane? So now I'm looking at my 3D space here, right? This is R3. right? Now in R3, the XY plane still exists within R3, right? This is this kind of horizontal plane here, this tabletop. And remember, it's kind of like, it's this horizontal plane here. And it goes off in all directions, right? It goes out infinitely far in all directions. Well, in these 4 directions. Okay. So this XY plane still exists here in R3, right? And that I just call that my XY coordinate plane, okay? Okay, so what do you notice about the points in the XY plane, right? What's in common with all these points? What's the Z coordinate of all these points? All right, let's pick just a bunch of points in the XY plane. Well, 2, 4, zeros in the XY plane, 1, 7 zeros in the XY plane, 100,000, -0.9 zeros in the XY plane. The common feature is that this Z coordinate is 0 in all of them, right? And that's really the key feature of points in the XY plane. Now, there are also XZ planes, or excuse me, there's also a XZ plane and a YZ plane, right? And I've cribbed this picture from the textbook, okay? So let's look at this and focus on this left side, okay? So this XY plane, that's what we were just discussing. Okay, this is when the Z coordinate's equal to 0, right? Well, what if the Y coordinate is 0? What am I going to end up with if the Y coordinate is always 0 and then all my other coordinates can be anything? Well, let's see, this point has a Y coordinate of 0, as does this one and this one and this one and so on. So the collection of all my points where the Y coordinate is 0 is going to give me this XZ plane. And then similarly, what if the X coordinate is 0? I'm going to end up with points in this plane. Okay. So these 3 things we call the coordinate planes. Now, what are the equations of these planes? They have really simple equations, right? I think we'll talk about this a bit later, but we can go over the special case here, right? Remember when we were drawing like vertical lines in R2? Okay, so let's say I wanted to draw a vertical line in R2. Okay, let's say I wanted to draw this vertical line going through the X coordinate 2, right? The equation of that would just be X equals 2, meaning all the points whose X coordinate is equal to 2. That gives me this vertical line. In a similar way, okay, this XZ plane is all the points whose Y coordinate is equal to 0. So that XZ plane has an equation Y equals 0. This XY plane has an equation of Z equals 0. And finally, this YZ plane has an equation X equals 0. So notice the equations of these planes. It's basically the letter that's missing here, equal to 0. Little trick. Okay. Quickly, projections. This, I was talking to another professor recently, and he had a quibble about calling these projections, and he's right that they're referred to as projections, but we're going to see a more rigorous definition of projections later. But let's say I have a point in R3, okay? So let's say I have, in particular, the point 3, 6, 4. And let's say I want to find a quote-unquote version of that point on the coordinate plane, the XY plane. Okay, so let's see, I have 3, 6, 4. What would that look like? I'll move 3 units along the X. You know, 6 coordinates along the Y, and then 4 units up, right? So maybe that point's there. Something like that. Okay. Now, let's say I want to find its projection onto the XY plane, meaning I basically just want to find a version of this point that is confined to the XY plane. How could I do that? Remember, the XY plane is all the points whose Z coordinate is 0. So let's just make this 0. Okay, what point would that give me? Well, it would give me that point down there. So this point I call the projection. If we label this point A, okay, so this is A and this is B, I could say that B is the projection of A onto the XY plane. Now I've projected onto the XY plane. We could also project this point onto the YZ plane or the XZ plane. Okay. So basically, if I want to project a point onto a particular plane, like the XY plane, I just make the Z coordinate 0. XZ plane, I make the Y coordinate 0, and so on. So just a quick little note. Again, this is not a very good definition of projections, but you might see it in the homework. Now let's talk about surfaces in R3. So just basic surfaces, kind of basic curves. As we saw earlier, okay, these, the surfaces, basically the graphs of functions, they're going to have the form f of xy equals z. Okay, that's going to give us a surface in R3. And a quick note, okay, remember in R2, we usually had f of x equals y, right? For example, let's consider a line. Y equals, 3x plus 4. But sometimes what I would do is I would kind of move all my variables to one side. And I would have a constant on that side. So we could rewrite these equations as, this equation fx equals y. I could rewrite that as, f of x, y equals a constant c. Okay. So sometimes you'll see that for this higher dimension as well. The kind of standard is to write these higher dimension functions as f of xy equals z. But sometimes you'll also see f of x, y, and z is equal to some constant. It's just a rearrangement. So let's talk about some simple surfaces, some in their equations. Okay. So this is kind of rehashing what we did with the planes, but let's kind of take a closer look at it. In R2, if I had the equation x equals 5, what would that be? Again, that's just a vertical line, right? It's all the points whose x coordinate is equal to 5, which gives me this vertical line here. Okay. So again, I interpret that as all points in R2 whose x coordinate is 5. And in set notation, I could write that like this. Okay, all the ordered pairs, all the x points x, y, such that x equals 5. Let's use the same equation. What are the points in R3 whose x coordinate is equal to 5? Well, let's find 5 in our 3 dimensions, okay? And now, what are all the points in this 3-dimensional space whose x coordinate is equal to 5? Well, let's just try and, let's find some points. Well, let's see. If I had like kind of a line in this plane going through 5, well, let's see. This point has x coordinate 5. This point has x coordinate 5. These over here have x coordinate 5. And what about a vertical line going straight up? Okay, well, this x coordinate is 5, this x coordinate 5, so on and so on. Okay, so what does this give me? And then, this gives me a plane, right? Think about the kind of plane formed by these axes I've just made through here. This plane here, right? And going off in all directions. All these points on this plane, they all have x coordinate 5. So instead of having a line, a vertical line, now I have a plane. Let's clean it up a bit. So basically now I have a plane going through there. Okay. And if I had been given the equation, let's do another example. If I had been given the equation y equals -1, what would that look like? Well, y equals -1. Well, let's find y equals let's find -1 on the y-axis. That'd be here. So what are all the points whose y-coordinate is -1? Well, I can go off in this direction. Y-coordinate is still -1. I can go off this way, and then I can go vertically, right? And I can go off to the right and then vertically to get to that point, so on. So again, I have, this plane, this time passing through y equals -1. Okay. So these are kind of the most simple equations we might see. Just like in R2, these would give us very simple lines. These give us very simple planes. Okay, that's just a simple plane in R3. Okay. Now, quick note, if you're just given an equation like x equals 5, how do you know if how do you know if it's a vertical line in R2 or a plane in R3? Well, it's all about context, right? If the problem gives you, if you're working on a problem and everything's dealing with R3, well, then this equation should be in R3. Okay. If the context of your problem is in R2, then it's going to be a line, right? So it's all just about context. And usually it'll be stated explicitly. So now let's talk about slightly more complicated surfaces with slightly more complicated equations. What if I have multiple equations defining a single surface? Maybe I'm trying to draw a surface, and I'm told, okay, these two equations define my surface. What would this surface look like? How would I figure that out? Basically, what you're going to do is just draw these one at a time. And I would say, let's see, I know this is the equation of a plane, right? I would leave that until last. I'm gonna draw this one first. Okay, what's x squared plus y squared equals 1? Okay, well that's if I was in if I was in just the xy plane. Forget about R3 for a second. If I was in just R2, what would that look like? X squared plus y squared equals 1. Well, that's a circle with a radius 1, right? Centered at the origin. Okay. So if I was in the xy plane, it would just be a circle, right? And then what else am I told? Well, I'm told, well, z is equal to 4. Okay. So I should move up by 4. Okay. And so I would have a circle that goes around the z-axis of radius 1. And that is my graph, my surface. So it's actually really simple. It's not even like a kind of, it's not really a surface with extra dimension. It's just a circle, but it's a circle raised up by 4 units. Here's another way to think about it. Okay. If I was going to draw x squared plus y squared equals 1, okay, as I said, okay, if I was just in the xy plane, that would be just a circle, right? Okay. But this equation here doesn't tell me anything about my z coordinate. So as of, if I'm just looking at this, my z coordinate can be anything. So I'm on this circle, my z coordinate could be anything. So it could be up here, it could be down here, and so on. So really, if I just had this equation, my object would be a cylinder that goes up forever and down forever. Okay. So it's a cylinder of radius 1. And then I'm given the additional equation, well, z equals 4. Well, what is z equals 4? Z equals 4 is the plane, right? Let's say this is 4. Z equals 4 is the plane that cuts through that point. Trying to make this look good. Let's say it goes back here. Okay. So I have this plane at z equals 4. Okay. And that z equals 4 kind of takes a slice out of my cylinder. And it really, my surface is just where these both these equations hold, right? So that is a very narrow intersection. Okay. It really just ends up being, let's see, it wouldn't be this. It wouldn't be any of this cylinder. It would just be, it wouldn't be any of this cylinder up here. It would really just be where this plane intersects that cylinder. So I'm just left with this circle. And this is something that's in the textbook as well. So maybe if you don't like my horrible 3D drawing, you can check that out. I would just be left with that circle up there at elevation 4. Okay. Now let's check out some other surfaces. How about y equals x squared? And again, I want to graph this in R3, but it might be helpful to first graph it in R2, okay? So y equals x squared, well in R2, right, this is R2. In R2, that's just a parabola, okay? So let's try and graph that in R3 now, okay? Well, let's start by graphing it in the XY plane, okay? So if I was just restricted to the XY plane, let's see, remember this is the positive direction, this is the positive direction. So I should orient it correctly. So it would look like this, right? Oops. It would be a parabola in the XY plane that looks like that. Okay. Now, if this is my equation, y equals x squared, z could be anything, right? This doesn't say anything about z. There's no restrictions on z. So my z could be z equals 0. That would give me just this equation in the xy plane. Or z could be 1. Okay, so z could be up here. Okay, or z could be -5. So down here. So really, my surface is this kind of parabola that stretches vertically, right? And it's just a shell. It's just, it doesn't have any thickness to it. It's just kind of the shell, and it goes off in these directions forever. Okay. Okay, so those are some basic shapes, and try and draw some of these yourself. There's plenty of problems in the textbook about drawing these simple surfaces, and we're going to see more of this in later sections. But these are just the basic shapes, basic formulas, basic surfaces. So now let's move on to distances and spheres, and this should be the last section of last part of this section. So think about distance in R2. Okay. So let's focus on R2. Let's say I have this point X at coordinates X, Y. Okay. What is this distance here from the origin to that point? Okay, what is that distance there? How do I find that? Well, there's a distance formula, right? D equals square root of X squared plus Y squared. And really, that's just the Pythagorean theorem. That I could consider this this point as being a triangle. This distance is like the hypotenuse of a triangle. What's this length? Well, that's the X coordinate. What's this length? It's the Y coordinate. So by Pythagorean theorem, the length of this side is square root of X squared plus Y squared. So that's where my distance formula comes from. And what if, so right now we had a point at the origin, right? Okay. What if what if I don't want to find my distance starting at my origin? What if I want to find my distance between 2 points? Let's say, let's reverse this, make it nice. What if I wanted to find the distance between x1, y1, x2, y2? What's that distance? Well, there's again a formula, right? This is my formula. And again, that's just the Pythagorean theorem, right? The distance here is the hypotenuse of this triangle. Well, what's the length of this side? It's x2 minus x1. What's the length of this side? It's y2 minus y1. Okay, so that's where my formula comes from. Now, there's very similar formulas for distances in R3, and really for Rn in general. So just a quick note, we're doing everything for R3, right? But everything we've done so far and 99% of what we do in this course is going to be true for even higher dimensions, which we could abbreviate by Rn, where n could be 4, it could be 7, it could be 100,000. Everything we've done so far is still true for those higher dimensions. The only problem is we can't really picture those higher dimensions, right? R3 is about as complicated as we can imagine. So we're just going to stick with R3 just because that's the easiest thing to picture in this course. Okay. All right. But what is the distance from the origin to this point in R3? Can we get some sort of formula? Let's say this point, okay, it's up here, boom, we got a 90-degree angle here, kind of like that, if you can picture that. Okay. What is the distance from the origin to that point X, Y, Z? Well, again, we could use Pythagorean theorem, right? We want to find this distance here. So first of all, okay, well, this distance here, if I knew the length of this side and the length of this side, I could find this side, right, by Pythagorean theorem. Okay, well, let's go piece by piece. What's the length of this side here? Well, I know this is kind of a, now I can have a triangle in this plane, okay, which is the XY plane. Well, this is the hypotenuse of the triangle whose, let's see, the distance this way, this direction is the Y coordinate. The distance going this way is actually my X coordinate. So maybe this is like point negative 2, 4, 4, something like that. So this point, this y coordinate would be 4, this x coordinate would be negative 2. Okay. So I can find, I have enough, if I know my x, y, and z coordinate, okay, this is my y. I know this length, so I can find this length here, okay, by Pythagorean theorem, okay. And similarly, I can find this length here. That is, well, that's just going to be my z coordinate. Okay. So I know this length, okay, and I know this length here. Let's see. What is this length here? This length here is square root of x squared plus y squared, and this is z squared. So that length that I'm looking for, okay, should be square root x squared plus y squared squared plus z squared. And if we simplify that, that's x squared plus y squared plus z squared. Okay, so it seems like, all right, if I want to find the distance from the origin to some point in R3, it's a really simple formula. It's just x squared plus y squared plus z squared. So almost the exact same as my formula here. I just need to add in that z coordinate. Okay. And what about if I, instead of starting at the origin, I want to find the distance between 2 points. Okay. Again, it's going to be very similar to the two-dimensional analog. Okay. In 2 dimensions, it was x2 minus x1 squared plus y2 minus y1 squared. In 3 dimensions, it's going to be x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay. And it's the same process we did here. Okay, we're just finding triangles. It really is just a repeated use of the Pythagorean theorem. So now let's move on to some spheres, okay? These are another simple shape in R3 that we need to get comfortable with. So let's again start by considering what we're familiar with, R2. Now recall circles in R2 are essentially defined in terms of radius, right? In terms of distance, okay? Here's an equation of a circle in R2, right? X squared plus y squared equals 4, okay? Well, if x squared plus y squared equals 4, we have, if we take the square root of both sides, we get something that looks like the distance formula on the left side, and then we get 2 on this side. So really what this equation is saying is, okay, if we look at it if we convert it to this form, we're talking about all points whose distance from the origin is 2. Okay, that's the kind of geometric intuition behind this equation. Okay. What about, before we move on to R3, we could also, this was for a circle centered at the origin, right? And remember, this is, for example, an equation of a circle centered at some point, in this case, 2, 3. Okay, so this is the equation of a circle centered at 2, 3 with a radius 3, right? And we can again see this if we take the square root of both sides of this equation, okay, what we end up with is, okay, we're saying here we have like a distance formula, and we're saying distance is equal to 3. So we're saying all the points x, y that are 3 units away from the point 2, 3. So again, some intuition behind the formula for a circle. Now, can we get something similar in R3? Okay. What would x squared plus y squared plus z squared equals r squared be? Okay. This is going to be the equation of a sphere centered at the origin with radius r. Okay. So again, if we started with this equation, let's explore why this is. If we took the square root of both sides of this, what would we end up with? X squared plus y squared plus z squared equals r, right? Okay, so what is this side? That looks like our distance formula. It's saying, okay, distance from origin in this case is equal to r. So this is all the points x, y, z that are r units away from the origin. Okay, so if we graphed that, forget about what this shape is. If we just graphed all the points that are r units away from the origin, what would that look like? Okay, so I have a little R3, okay. Let's say our R is, in this case, 1. So all the points that are 1 unit away from the origin. Well, this point's 1 unit away from the origin, so are all these points. So I can start by drawing a circle in the, what plane is that? That's the YZ plane. And then I could draw a circle in the XZ plane. And really, I end up with this sphere. Okay, so all these points give me a sphere in R3 that are 1 unit away from the origin. Now, similarly, I could move the center of my sphere around. Okay, if I have x minus a squared plus y minus b squared plus z minus c squared equals r squared, that's going to give me the equation of a sphere centered at the point A, B, C with radius r. And hopefully why that works is clear. Now, what is this whole mess? Let's look at some examples. So first example would be x squared plus y squared plus z squared plus 4x minus 2y plus 4z plus 5 equals 0. What does this whole mess give us? Okay, maybe we're told that this is the equation of a sphere. Okay, let's say the problem also says, find the standard form of this equation for the sphere. Okay, so this is telling us, all right, this is the equation of some sphere, and this is the standard form of this. This is how we like to write these equations of spheres. So basically what this problem is telling us is, okay, they give us this equation for a sphere, and they want us to rearrange it into this form. Okay, so how can we do that? Well, let's start by pairing up all our x's with our x's and so forth. Okay, so really I could arrange this equation into x squared plus 4x plus y squared minus 2y plus z squared plus 4z. Then let's put the equals 5 here. Oh, no, sorry. Plus 5 equals 0. And you know what? Let's go ahead and move that 5 to the other side of the equals sign. Okay. So I have all my variables equals -5. Now, I have x squared plus 4x. Okay. Can I somehow get that to look like x minus a squared? Yeah, I can. By completing the square. So remember completing the square. Okay. So let's look at this x squared plus 4x, and let's try and get that to look like x minus a squared. Let's turn this into a perfect square. How can I do that? You remember, if you take this number divided by 2 and square it, and put that there, and then subtract it away just to keep everything even, this part will be a perfect square. Okay. So let's just put that in parentheses for a second. Okay. Really, I haven't changed anything, right? I've added 4, I've taken away 4. So I still have the same equation. Okay. And then let's kind of rewrite this so it's a bit neater. Okay, I got this. Let's do the same thing here. How could I turn this stuff into a perfect square? I'm gonna take this, divide by 2 and square it. Okay, so plus 1. And then I subtract 1, right? Okay, again, I haven't changed anything, but now this is a perfect square. And let's do the same thing here. Again, let's kind of rewrite this so it's a bit neater. Okay, so making a perfect square. Okay. I've added 4, I've taken away 4. All right, so the stuff in parentheses now. What is that stuff in parentheses? Well, this term here, what is that perfect square? That's x plus 2 squared. Then I have minus 4, right? And what about this term here? Well, that would be what? Y minus 1 squared minus 1, right? And then what's this term here? That'd be z plus 2. Minus 4 equals negative 5. Okay, so now this is looking a lot like my standard form of my equation. The only problem is I got some extra numbers on this left side. So let's just move them all to the right side. Okay. Let's see, negative 5 plus 4 plus 1 plus 4, right? So 4. Okay, so this is the standard form of my equation for my sphere. So it's a sphere centered at what? Negative 2, positive 1, negative 2 with radius 2. Okay. Now, that's one example. Let's look at another example. So now, instead of having an equation, I have an inequality. So I have x minus 2 squared plus y minus 1 squared plus z minus 1 squared is less than or equal to 4. Well, again, let's consider the kind of a two-dimensional case. If I had, let's say, x minus 1 squared plus y minus 1 squared is less than or equal to 1. What is this? Well, if this was an equal sign, this equation would be a circle. If this was an equal sign, this would be a circle of radius 1 centered at the point 1, 1, right? So maybe a circle that looks like that. But since it's less than or equal to 1, it's all the points, okay, x, y, such that when you plug them in there, their answer is less than or equal to 1. So really, this is the solid disk, okay, of points here. It's not just the outer shell of the circle. It's all the points inside. Okay. Now let's kind of take that idea and scale it up to 3 dimensions. Okay. Again, if this was an equal sign, what would this equation be? Okay, I'd have my 3 dimensions. Okay, it'd be a sphere with center at, let's say, 1, 2, y equals 1, z equals 1. So let's say, okay, so let's say that's where the center of the sphere is. Okay, so a sphere with that center. And radius, what, 2? Okay. So it's a sphere like that. But then instead of an equal sign, I have an inequality. So it's all the points that satisfy this inequality. So this is going to be the solid ball. Okay, so this is like a solid three-dimensional ball. So I apologize, my 3D drawings are horrible. You're going to have to kind of follow along and try and imagine. But instead of having a kind of empty sphere, we have a solid ball. Okay. So that would be what that inequality is. And really, that's the end of the material from 12.1. We're just starting to work in R3 and drawing some simple surfaces and trying to get used to working with those surfaces and points. In later chapters, we're going to start doing more complicated things with functions and derivatives and integrals. But first, we got to just figure out how this three-dimensional space works.